Our project presentation topic is design and simulate a PV system to power a community-sized water filtration system. So this is the outline of our presentation where we will be looking into different stages of a project in detail. So coming to the introduction, the main objective of this project is to design and simulate a PV system to power a community-sized water filtration system for the people of Black Tickle Domino, where 126 residents reside, and these people have to travel around 2 kilometers to get water for their utility purposes. These are the research papers which we have gone through for our project work, and our main conclusions were that around 80% more daily PV energy was utilized when using a solar tracking system, and 10% more PV energy was used when the panels were in cool condition. And also, it was concluded that photovoltaic based reverse osmosis is a very good optimal solution, and which has a potential to reach to 2 to 3 US dollars per meter cube when using this technology. So these are the types of PV cells, and we have three types of PV cells: monocrystalline, polycrystalline, and thin film solar cells. Of these, monocrystalline PV cells are the most efficient and the expensive ones when compared to the other two. Reverse osmosis system. In this system, the contaminated feed water is sent through different stages where the water is filtered and ready for usage purposes. In the first two stages, the water is sent through a set of filters where the particles and the sediments are removed from the water, and in the third stage, the water is pressurized and sent through an RO membrane where the water is cleaned and all the impurities are removed, and the water is then stored into a storage tank where it is ready for usage. So these are the characteristics of our selected site. The selected site was Herring Cove Pond, which is around 1 kilometer away from the Black Tickle community. And the bore depth of this pond is around 143 meters. Based on reports, the water from this pond is safe as it does not contain any chemical and mineral substances, and it is fit for consumption. Alright, so next we have the site solar potential. As you can see in the figure that the selected site has an average solar potential of 2.97 kilowatt per meter square per day, and the average clearness index is 0.46. The picture is taken from the Homer software so that we can depict how does these parameters look like. Right, the next thing that we have is to how the selected water sources and the requirement for the water. So average Canadian drink around 272.55 liters, and but the issue is that the Black Tickle community consumes as low as only around 88.2 liters. So in order to fulfill the needs of the community at the required drinking level and consumption level, we would require 34 meter cube of water per day. The diagram 6 shows the schematic that the pump is being used to bring the water to the level ground to tank 1. Then it is passed through the reverse osmosis system and eventually to the clean water tank and then utilized by the community. Next, we have the calculation of the energy. In order to calculate the total dynamic head, we have the formula which is displacement plus the height of the beams times the loss which is in the LOs. So the hydraulic power was calculated using the formula of density, gravity, total dynamic head, and the flow rate. And it was divided with the efficiency. So we assume the efficiency of the pump to be 60%. And we got the shaft power, which is around 5.2 kilowatts required for bringing up the water from the ground level to the first tank. On the basis of that, we selected the loads. So in order to achieve the required capacity of 37.4 gallons per minute, we selected a system which is of reverse osmosis, which takes 12 kilowatt of load. The pump was selected of 7 kilowatt, which is a submersible pump, and which can easily provide a dynamic head of 134 meters at the required flow rate. And the miscellaneous 1 kilowatt load is because of the lightning and control equipments that will be there in the system. So eventually the total load of the system turns out to be 20 kilowatts. Finally, the system was designed in the Homer Pro software. You can see the schematic diagram on the right hand side of the screen. The best condition turns out to be that the load has 80 kilowatt hours per day with a peak load of 35.1, and there were like 32.9 maximum power panels that were required. The inverter voltage was kept at 48 volts, which is a fixed 48 volt. The results are shown. The first figure depicts how the monthly electric production on the PV was produced using the PV was produced. The second one shows this battery state of charge, and as you can see that majority of the time the battery is in good health, which is near the 100%, which is the red part.
The third figure, which is figure 11, depicts the comparison of the load with relate to the solar panel and the relationship of the battery. So as you can see, when there is excess power, the battery is being charged, and when there is no power from solar panel, the battery is supplying the power. Last but not the least, the figure 12 summarizes all the electrical parameters that came out as a design analysis of this interval. The next one is the economical analysis, which is about the cost analysis and the cost parameter summary. So as you can see that the major cost of this whole system turns out to be the dollars itself, which is contributing to around 50% of the cost of the system. Overall, we have a net present cost value of $219,000, whereas the cost of energy turns out to be just $0.58, and the operating cost is 1,904 per year. So overall, there is a high initial cost value, but over the period of time, it will be recovered because of the free energy from the renewable energy sources.
I'll be speaking on the dynamic modeling of the system. The whole system was modeled in MATLAB and it consists of the PV array, the converter, the inverter, the battery, and the reverse osmosis load. For the PV array, we used a system with 79 strings. For the converter, it consists of the capacitor, the inductor, the switch, and and another capacitor. So the capacitor's capacitance was 0.06 Faraday, and while the inductance was 0.02 Henry. The battery used was a lead acid battery with a nominal voltage of 110 volts and a rated capacity of 1370 Ah. The pulse generator is connected to the converter with a switching frequency of 1500 Hz. A lead acid battery is connected to the inverter and also to the converter. So the PV provides power to the converter. The converter converts voltage from a lower voltage to a higher voltage. So the converter is a boost converter, and the boost converter charges the battery. The inverter, which is connected to the battery, feeds the load, the reverse osmosis load. This system does not operate on MPPT. For the dynamic results, the dynamic analysis for the PV panel, the voltage, as, as you can see, that it reaches stability, while for the boost converter charge results, the result shows that it keeps charging and it keeps boosting the input voltage. So they all ascertained stability. While the AC waveform results from the inverter, AC waveform is a square waveform with harmonics, and yeah, that's our dynamic results showing that this system was suitable for this setup. For the control unit section, because of the pumping water from a well, from a well to a tank, we need to control the pumping and also to make sure that this water is not being wasted. So because of that, a solar powered water pumping system for a water well consists of a PV panel as the voltage just stored in the battery. So we are controlling the voltage stored in the battery, not from the PV panel. Then the DC motor, the pump drive, and the variable speed pump. We are going to control the pumping from a reserve to a tank such that at a certain height level, the at a certain height level, the pumping action is stopped. Our control objective is to control the solar power pump water pumping system such that at a particular water level in the tank, the system maintains a certain level, and this will be done using a PID, mostly a feedback controller. The control system will be a combination of a PID so that it maintains the water level and slows down the motor unit when the tank is full. The pump should be turned off when the tank reaches its desired certain level, since its speed is being reduced so it cannot pump enough water. For the water level controller design, we first modeled our system and modeled our system in MATLAB. We got our steady state equations and we used the PID controller with the set points of 1500. We have three states from our modeling: one input, that's the voltage of the battery, and three outputs, that's our current, our speed, and also our height. Our water level controller design results shows that at at 1,500 meters, the motor current is being stabilized to a point, is being controlled, while at the same height level, the speed control is being controlled to a certain point. You can see that there's a down slope of the motor current and also the speed current, because the motor current is the one that controls the speed of the pump. So their dynamics are alike. For the water level controller, at the same height, the PID successfully cut off um, the water. There was no overshoot, and the water level was controlled and maintained. This analysis was done using a load variation. The load was varied between 23 volts to 26 volts to show to check the stability, and also to check if the PID is going to be suitable for this design, which at the end of it all was successful for our projects.
So this is our system protection control design. So here the submersible pump and the feed water pump are powered through batteries, which are charged by the solar panels. The submersible pump and the feed water pump are protected by one overload relay, which senses for any abnormal conditions like overcurrent, thermal overload, phase imbalance, and undercurrent. We have also installed open-close walls at different positions to isolate the system for any maintenance and emergency situations. Flow rate sensors and pressure sensors are also installed to monitor the process flow throughout the system. And high level switches and low level switches are also installed on the brackish water tank and the clean water tank to monitor the water levels. So in this slide, the system protection control schematic functions are elaborated, and now we'll be looking into one by one. The submersible pump A and the feed water pump B are protected by an overload relay, which senses for any abnormal conditions like overcurrent, thermal overload, phase imbalance, and undercurrent, and trips the pumps in any of these abnormal situations. Then moving on to the brackish water tank, we have two level switches installed on the tank, one high level switch and one low level switch, which continuously monitors the liquid levels in the tank. When the liquid level reaches the high level switch, it initiates a partial shutdown of the system by first sending an stop command to the submersible pump A and followed by closing of the valve B. In this situation, the remaining of the system remains in operation. Then moving on to the RO membrane, this protection function considers the differential pressure across this RO membrane by taking the feedbacks from the pressure sensor 9P, which is at the inlet of the RO membrane, and the pressure sensor 11P, which is at the outlet. So if the differential pressure reaches a defined set point, an emergency shutdown signal is initiated and the whole system is shut down. This condition implies the healthiness of the membrane. Then moving on to the reject water outlet. This protection function mainly monitors on the productivity and the efficiency of the system by taking the input feedbacks from the flow rate sensor 12F, which is at the RO membrane outlet, and also the flow rate sensor 19F at the reject water tank. And if the efficiency of the system falls below 50%, the emergency shutdown signal is initiated to shut down the complete system. And moving on to the clean water tank, same like in brackish water tank, we have two levels which is installed, high level and low level. When the water levels reach the high level switch and holds for 15 seconds, the level switch initiates a signal to trip the whole system. And now moving on to the conclusion, this project summarizes an effective method and economical method to provide clean water to the community of the Black Tickle. And also this was achieved by optimizing the whole design in Homepro software. This system is based on solar power, which is a clean renewable energy source. That means there is no carbon footprint left on the environment, because there are no emissions. And because also if there are emissions, they have little impact on the environment. The system output depicts that we can get a maximum power of 32.9 kilowatts from the solar panels, and then battery arrangement of 72 batteries, sets of 4 strings is sufficient to completely run the system. And the dynamic modeling results can show that the energy acquired from the solar panels is sufficient enough to feed the RO system load and all the other major components and the miscellaneous loads. And moving on to the control part, we also designed a level controller which can monitor the liquid levels of the system, and protection schematic was also designed to increase the reliability of the system and maintain an high efficient output. Thank you.